Dear students, today our topic is rate theory of chromatography. This is most important topic that comes in exams. Now, rate theory of chromatography describes shapes and breadths of illusion bands in quantitative terms based on random walk mechanism for migration of molecules through a column. Now, if you examine this chromatogram, you will see that illusion peaks look like Gaussian or normal curves. These looks like Gaussian or normal curves. Now, typical Gaussian shape of a chromatographic band can be attributed to additive combination of random motions of various molecules as they move down the column. It means that formation of these Gaussian curves depends upon random motion of molecules as they move down the column. Now we assume following discussion that a narrow zone, this is a narrow zone that has been introduced so that injection width is not the limiting factor. Injection width means width of injection of the sample. That is not only the limiting factor for determining the overall width of band that elutes. It is important to realize that width of eluting bands can never be narrower than width of injection zone. It means that it has a relation with the width of injection zone. Now consider a single solute molecule as it undergoes many thousands of transfers between stationary and mobile phase during elution. When we consider a single solute in a sample, then that solute have a lot of interactions in terms of transfer among stationary and mobile phase during its elution. So residence time in either phase is highly irregular. It may have more time in stationary phase, less time in mobile phase, or more time in mobile phase and less time in stationary phase. Its residence time is irregular. Transfer from one phase to the other requires energy. It requires energy when it moves from one phase to the other phase, and molecule must acquires this energy from its surroundings. Of course, it will get its energy from its surroundings from moving down the column. Residence time in a given phase may be transitory after some transfers and relatively long after others. Residence time in one phase may be longer as compared to the other phase. Now, movement down the column can occur only while the molecule is in the mobile phase. Of course, it will move down the column when it is in mobile phase. When it is in stationary phase, it will not move down the column. As a consequence, certain particles travel rapidly by virtue of their inclusion in mobile phase. They have more attraction in mobile phase as compared to stationary phase, whereas others lack because they happen to be incorporated in the stationary phase for a greater than average length of time. More time they remains in stationary phase as compared to mobile phase. Result of these random individual processes is a symmetric spread of velocities around the mean value. Of course, around mean value there is a symmetric spread of velocities that leads to formation of Gaussian curves. The breadth of a zone increases as it moves down the column because more time is allowed for spreading to occur. Of course, its breadth increases. Breadth increases when it moves down the column. It has narrow breadth, then it means less time is required. When it has more breadth, then it means it has more residence time in moving down the column. Understand? Narrow breath means it has little time, residence time, and more broader breath means it has more residence time. Zone breath is directly related to residence time in the column and inversely related to velocity of the mobile phase flow. This is all about our rate theory.